Well, hi everyone, I'm Tess. I'm over at MIT, and I work a lot with, well, myself and my research group, we work a lot with symmetry-equivariant neural networks. And sometimes these types of neural networks get a bad rap for being very confusing. So I thought I would present some intuition for the data types and interactions in these types of models. I'm going to be specifically talking about Euclidean symmetry, which I'll introduce in the next slides. But actually, a lot of these intuitions actually transfer over to just about any symmetry group that we're typically interested in, especially for physics. So without further ado, I'll go ahead. Okay, so first I want to motivate why we might want to use neural networks imbued with symmetry. So I'm a materials physicist by training, but I'm in an EECS department. And my motivation is the following. So when we describe physical systems, for example, atomistic systems, we typically want to describe, where the atoms are in 3D space. And to do this, we'll use a coordinate system, basically as, where we're going to base our metric. But let's say I have these three benzene molecules. I could use coordinate system 1. I could use coordinate system 2. It's the same physical system, just a different description. And my choice of coordinate system is fundamentally arbitrary. And we can always transform our coordinate systems using the symmetries of 3D space. So 3D translation. So as long as we're not going too fast, 3D translation, 3D rotation, and inversion. So why might this be problematic when you want to use machine learning on this type of 3D data? Well, the problem is that traditional machine learning sees, the description from coordinate system 1 and the coordinate system 2 is completely different, unrelated. It would have to learn how these things are related, and that's rather inconvenient. Whoops, sorry. Okay, so, but if we don't want to wait for our neural network to actually learn these symmetries, and instead we want it to be able to focus its precious weights on things, for example, like learning quantum mechanics, what we can do is we can imbue our neural network with these symmetries so that even without training, it's able to understand that coordinate system 1 and coordinate system 2 are being used to describe the same system of molecules. And so I'll be talking about Euclidean neural networks, which basically have this property. So one more definition that I want to give is the difference between what I'm going to say an invariant model and an equivariant model. So an invariant model is something that takes the approach saying, hey, these coordinate systems are like really annoying because we actually have to, take all this care of dealing with them properly. Why don't we just get rid of the coordinate system altogether and describe our system in a coordinate-free way? So what you might do is you might try and use invariants of your system in order to describe it. Things like pairwise distances, angles between three objects, and there's many other ways to do this. So this is one interesting approach, and it can be very effective. But in this talk, I'm going to talk specifically about how do we keep the coordinate system around and how do we handle it properly. And most importantly, that if we have some input or output that changes predictably under a change of coordinate system, that neural network is going to guarantee that those changes will happen. Again, without training, it's built into the very fabric of the model. Also, if there's any questions with anything I'm saying, please feel free to raise your hand, unless Marisa says that's not a good idea. That's fine. Okay, cool. So if folks raise their hand, I'm happy to take any questions. Any questions so far? Awesome. Let me know if that changes. Okay, so just to give some additional examples of what properties these types of neural networks have, let's say we were interested in the task of molecular dynamics, where we want to, given an arrangement of atoms, predict the forces on those atoms. So let's say I've trained a network and it's predicting these forces on this molecule. If I show the network the same molecule rotated, the forces predicted will rotate appropriately. Furthermore, if I have recurring motifs in different locations and orientations, the model not only has global equivariance, it has local equivariance. Usually this is done with something like a convolutional filter. So if I have this rubidium manganese chloride crystal, and I have these little octahedral motifs where manganese is octahedrally coordinated by chlorine atoms, you can see these octahedra are basically the same pattern, but they're in different orientations. The model will be able to recognize that these Basically, these little local environments are the same, but then as it can see further out, if you're doing something like message passing, it'll also be able to see that these are the same pattern, but they're rotated in different orientations relative to each other. So you kind of get the both aspects of it. Here's a more complicated example. And the reason why I like to show this example, which I'll explain, is that it kind of shows that while, when we think about rotating 3D objects, 3D rotations can seem fairly simple. But once I'm dealing with higher order tensor features, these rotations can actually seem pretty complicated. And it's really nice to not have your network have to learn this. So what I've got here is I've got a water molecule, and this water molecule is rotating. And over here, I have its electronic Hamiltonian done at the level of density functional theory. So the way that you read this matrix is that the rows and columns are electronic orbitals. So we have electrons occupying specific molecular orbitals. So we have the orbitals on oxygen, the orbitals on one of the hydrogens, and then the other hydrogen. And it's sort of the interaction across these orbitals. And as this is rotating with it. So this is actually the same Hamiltonian, or like it means the same thing, but just because I'm changing my coordinate system, this Hamiltonian matrix is changing wildly. So we really don't want our model to have to learn how to do this, because it's hard enough just, getting to learn quantum mechanics. Now this is a simple system, but we want to go to very complex, very large systems. So hopefully this kind of hits home for your applications in mind, that you too may have complex tensors that you wish to model. All right, so I think in the kind of broader community of atomistic systems, so these types of networks have been used in other places as well, but I know the atomistic system application's the best. What's really exciting is that as these models have been in the hands of more folks, people have done some really clever things to scale them to different systems. For example, there's currently a Gordon Bell finalist paper out of Boris Kaczynski's group, scaling molecular dynamics at the level of quantum mechanical accuracy emulated by an equivariant neural network, scaled to work on an HIV capsid. So that's pretty exciting. I'm wishing them a lot of luck for the final kind of competition. But these models are just generally very effective at capturing molecular properties, even things like phononic properties in the protein space for folding, scoring of RNA structures, docking, conformer generation, catalysis, so predicting energies and forces for heterogeneous catalysis, predicting magnetic orderings. So it's been really interesting to see that these models seem to be very effective for different atomistic systems, but there's still a lot to do. So if this is of interest to you, this is a great time to get involved. Okay, how am I doing? I have 21 seconds left. Oh, that's 21 minutes. I was like, wow. I mean, usually I'd take a long introduction, but not that long. One more thing before we go on to the intuition part. One thing that we're noticing, and this is across many different use cases, so whether it's for fitting charge densities of atomistic systems or whether it's for force prediction, we see this trend where if you compare invariant models, so the things that don't use coordinate systems, and equivariant models, the things that do, we notice the certain power law in terms of its data efficiency. So data efficiency is usually kind of mapped out in the following way. I take the log of my error across the log of the number of training examples. So as I get more and more data, my model should get more accurate. And what we're interested in here is that when we're in log-log space, these power laws tend to look linear. And what I want you to notice is not only is the equivariant model just instantaneously kind of more accurate, but what we're also seeing, it has a steeper slope. It's learning more quickly from new data. And if you are in a field like materials physics, which is rather data poor, at least compared to the combinatorially explosive space of atomistic configurations, this is a great benefit. And it might be one of the reasons why we're seeing these kind of early successes of these models. Furthermore, and this will make more sense later in the talk, but as we go to higher and higher order internal representations of the network, which is characterized in 3D space by these L's, which I'll explain later, we tend to see not only more of an offset, but possibly even basically a steeper slope. So this is still, we don't have like a working theory for exactly why that is. We have a lot of intuition, but this is something that's being observed currently in these models. Yeah. Sorry.
Thank you.
Like,
So in this picture, suppose I were to plot just non-equivariant or invariant neural networks, but with data augmentation.
Yeah.
Like, how should I think of the comparison? I understand maybe more flops, but just in terms of number of base.
Yeah. So, okay. So if you want to compare a non-equivariant model in these use cases with sufficient data augmentation, I think it is possible that you may be able, I think on the training set, you could definitely get just as good of accuracy, but I am not sure that you're going to get as good testing accuracy or validation, because I think what we've seen is that these models are a lot more robust. And I'm happy to talk in much more detail offline about exactly what is meant by that. There's been some specific papers that explore this. But I think it would be really nice to have those benchmarks. Very few people are willing to do those benchmarks because it's so nasty dealing with 3D coordinates. Yeah, so I don't think we have very good benchmarks, but my guess would be like you could probably achieve like some aspects of the accuracy, but I think you're gonna suffer from particularly the types of distributions in these data sets. Yeah. Another question over there?
So I'm curious about like how does the complexity grows with L max, and how if you plot log error as a function of computational time.
Yeah, so the complexity, it does not scale favorably. But that's kind of a very broad statement, and there's actually a lot of like tricks that you can do to make it not so computationally daunting. You know, these networks do have kind of a name for being like really expensive. I don't think that's a long-term thing. Like theoretically, like the reason why they're expensive is for reasons I'll actually talk about later when we talk about tensor products, but it's a great question. But I think it is manageable. And also you can bug one of my students, Mitt, who's in the front, and he can tell you a bit more why we have some hope for why things may not be as dire as you may have heard. One more question in the back too. Oh, sorry, I didn't see you.
It's okay. I just want to ask, do you have intuition for why the equivariant networks have a steeper power law than the invariant networks?
Yeah, so if they're given the same initial information, basically you have more types of interactions available to you. And this, again, will come up a little bit more when we talk about tensor products as to what's kind of going on under the hood and why it's just a richer operation. So basically, you have more ways of generating new information than you do with just scalars.
I have maybe a slight variant of the question you just answered, which is, I think like if the ground truth solution is within the model class, then you would expect that restricting the model class would like improve your slope and allow you to reach it more quickly. Whereas if the ground truth solution is outside of the model class, then you would expect to asymptote to a log error that is like higher than 0.
Yeah.
So I'm wondering, are you able to distinguish between whether maybe the invariant networks are just like asymptoting to a higher error, or whether they're actually like going to 0 but at a shallower slope?
Yeah, that's a great question, because it could be that the function you are trying to model is inherently not invariant, that you actually require some additional equivariant interactions in order to make the prediction. So that's definitely also possible. Yeah, so this is still, I would say, pretty early days, and I would love to discuss like better ways of benchmarking this phenomena. So this is kind of a broad strokes phenomena. Yeah, and it would be great to classify it better. Yeah, thank you for the questions. Okay, I think we'll continue on. Yeah, okay. So now I want to give some intuition for why this is. And basically, there's 3 particular ways in which these types of neural networks are different. from kind of your standard neural network. Part of it is that we don't just have numbers floating around in our networks, we actually have specific data types. Then there's also a different way that we interact data. We don't just do scalar multiplication, we do tensor products. And then last but not least, one thing that we utilize in these models is how we go about featurizing geometry, which is a lot easier to describe when we have pictures. Let's start with the first. So different types of data, if you have data that transforms predictably under rotation, then there's different parts of that data that will transform differently under what's called group action. So basically, this is applying the group to the actual data. So rotations and inversion, I'm just going to deal with those. Translation, we can discuss offline. So what's really neat is that no matter what your data is, if it transforms predictably under rotation and inversion, I can always break it up into pieces that can be described by two numbers, an angular frequency and a parity. So angular frequency, basically how quickly does the data change when I apply a rotation, and parity, if I invert space, x, y, z goes to minus x, minus y, minus z, does it flip sign or not? So any data, no matter how complicated of a function you've learned. Let's go through some examples. So let's go with angular frequency 0. So probably one of the things you're most familiar with are scalars. They don't change under rotation and they don't change under parity. This would be something like a classification label. If I was identifying things in an image like rabbits, that classification label is a scalar. Now it's kind of mirrored twin, if you will, is a pseudoscalar, something with odd parity. This would be like I'm classifying hands, but I'm specifically classifying that this is a right hand. And if I invert my coordinate system, it's going to turn into a left hand. So this is a pseudoscalar quantity. So in the same way of handedness in particle physics. Okay, let's go to L equals 1. So these are things that have an angular frequency that matches the rate of rotation. The thing you're probably most familiar with are vectors. Vectors we use to describe points in 3D space or forces. These things, they just change along with the rotation. And if I invert my coordinate system, they too flip. So x, y, z goes to minus x, minus y, minus z. Its mirrored twin is a pseudovector. Pseudovectors are actually rotation axes. And a really good way to see this is the following. So let's say, one way to define a rotation is to do a cross product. X cross y gives me z. I have my right hand rule. Now, if I were to invert x and y, I do, minus x cross minus y, I still get z. So that's the definition, or that's one way to think about a pseudovector, is the cross product is invariant under inversion. So you can use these for many things, but the most familiar thing is a rotation axis. Okay, I'll stop at L equals 2, but I think this one's really fun. So these things change at twice the angular frequency as a rotation. One example that I absolutely love is the even parity case, which is a double-headed ray. It is the thing that differentiates the x-axis, but doesn't differentiate plus x or minus x. So if you have a time-varying electric field, and you want to kind of average, what is that? You're defining a direction because it's ultimately oscillating between these two directions. So that's like one example of where you might want to use a double-headed ray. Its mirrored twin is something like a helix. And I have another example for this. So you may have heard of helices being left or right-handed. DNA has a handedness to it, and I don't remember which one it is. But we can do the same kind of example where we have x, and then we have y plus a little bit of z. And then when we invert that, we get minus x, minus y, and minus that little z. And so you can see that you end up getting a different handedness object. So you have a right-handed and a left-handed case. So you can keep going on and on to higher L. And I think what I want to give in your mind is that an L object has an L-fold symmetry. So this helix, you rotate it by 180 degrees, or this double-headed ray, you rotate by 180 degrees, and it looks the same. And then it's really just defining how that object behaves under parity. So why do we do this? So these distinct L and parity objects have another name. They're called irreducible representations, and they have this really beautiful property where if I apply any element of the group O3. And here I'm showing you actually a smattering of random elements of O3. And I go ahead and stack these vector spaces. So I'm just stacking a scalar vector space, a pseudoscalar, a vector, and a pseudovector. No matter my operation of the group, it has this block diagonal structure, which means these spaces are independent. They don't mix. They don't talk to each other. And what's super cool is that, again, no matter what data you give me, if it behaves predictably under your group, I can always re-express it as these irreps and recover this block diagonal structure. And this is really helpful. So it doesn't matter how complicated of a function you learn, as long as it predictably transforms, you can do this. I'll skip this point for now because it'll come up next. Okay, let's talk about interacting data. So what are all the ways we can interact? Let's say we just wanted to deal with things we knew, scalars and vectors. What do we get? Well, if I multiply a scalar times a scalar, I get another scalar. Simple. If I take a vector times a scalar, I still get a vector, but the scalar scales it up or down. It can't change the direction, and that's important. But what do I do with two vectors? So the most general operation is an outer product, which produces a 3x3 matrix. Notably, the 3x3 matrix does not have a single unique frequency. It does have a single parity, because odd times odd is even, but it doesn't have a single angular frequency. And this is because we can decompose it into our irreps. So I'm going to replace it with this O times, which is typically used for tensor products or outer products. And what happens is you can actually break this thing up into simpler pieces. So the dot product of your two vectors gets encoded as the trace of the matrix, which is a scalar. Your anti-symmetric part of the matrix is a pseudovector, notably, not a vector, a pseudovector. And so it's taken care of there, and that's from the cross product. And then what you have left over, the thing that the outer product contributes that the dot product and cross product do not, is this symmetric traceless product, this pure L equals 2 even object, so something that transforms like a double-headed ray. The reason why I show this example is that even if you only give your model scalars and vectors, you always have the possibility of generating these higher order objects or these different paritied objects and the things that you kind of normally think of as describing physical systems. They're already there. It's just up to you as to whether you get to harness them. So if you only use scalars and vectors in the internal representations of your network, you are by default throwing away these objects. Another way of saying that is if you only use scalars and vectors in your network, you can only use scalar multiplication of either scalars or vectors and dot products. That's what you're restricted to. Okay, I'll keep going. Okay, let's talk about the scaling of a tensor product. So a full tensor product is not computationally very friendly. And that's because it preserves dimensionality and it preserves information in some sense. So if I have an n-dimensional vector space and I tensor product it with an m-dimensional vector space, I get an n times m dimensional vector space. That's not great if you have a compositional type of function like a neural network. You're going to end up getting, let's say, n to the whatever dimensional vector space. So how can we deal with this in a learning setting? In order to maintain equivariance, I can only basically leave off dimensions that transform within themselves. I can only cleave off these irreps. Otherwise, I'm going to have some feature, it's going to rotate into a dimensional vector space that I cut out, and it won't be equivariant anymore. So in order to maintain equivariance, we throw out entire irreps. And so what we can do, and we don't have to do this live, we can do this as we design our models. We can decompose these things into irreps, and then we can decide to leave some of them off. This is obviously one of the simplest examples. As you have more channels and stuff, this gets more complicated. But this is why we do this decomposition, because if we drop out entire irreps, we know we're safe. Okay, 5 minutes, great. Let's talk about
a little bit more time because of the questions before.
Oh yeah, okay. Okay, hopefully I didn't go through this stuff too fast. We're doing okay so far? Okay, I see mostly smiling faces and nods, so great. Hopefully you're like, okay, so this is why these crazy people talk about irreducible representation so much. They're like the best thing ever, in my humble opinion, my unbiased humble opinion. Okay, let's talk about featurizing geometry. So as we use these Euclidean neural networks, our typical input is going to be some features in 3D space, and then, or I should say some geometry and then features on that geometry. So the example I always like to give is 2-point masses that have acceleration and velocity vectors. So this is the first part, but again, we don't just have numbers floating around in our neural networks. I have to tell them, or tell the neural network, what is this data? So I tell them, okay, I need to tell you the geometry, the feature, and the irreps that my data transform as. So the masses transform as scalars. The velocity and acceleration are vectors, and so they transform in a particular way. So this is how we do things in our Python package, E3 and N. We've encoded all the tensor product math, so you don't have to. And we have these irrep classes, which will be the first number is L, and the second number is either even or odd parity. So that's just what that code means. Okay, so one way to featureize geometry in a neural network is using convolutional filters, or at least some sort of function of geometry that then gets passed as another input to the network. There's other ways of doing this. And specifically, if you're making a Euclidean equivariant neural network, your convolutional filter is constrained to have a particular functional form. So convolutional filters are just functions of space. So just some queryable function. If it's on a grid, you don't need the R argument because you just have it on a fixed grid, but I deal a lot with points. So I prefer it in its full functional form. And what we can do is we can break it up into learned radial functions and angular functions, much like we do with the wave function of the hydrogen atom, not a coincidence. So the radial function can be pretty much anything, and then the angular function, we break them down as spherical harmonics. And there's a specific reason for this, but just as a reminder for spherical harmonics, for a given L, there's 2L plus 1 spherical harmonics of that L. One way to think about why there's multiple functions is that when you're in 3D space, there's more than one way to have an L-fold symmetry. You can have it in many different directions, and this is a complete orthogonal basis as you go to higher and higher L. Why are we using the spherical harmonics? Well, sorry, do I keep hitting this thing? We use these spherical harmonics, well, first of all, because they turn out to be what's called the basis functions of the irreducible representations of SO3. Well, it's a bit of a mouthful. In other words, spherical harmonics transform as specific irreps. So if you're dealing with O3 versus SO3, the biggest difference is that the parity of the spherical harmonics, they have a specific parity. So the L equals 0 spherical harmonic proportional to a constant is even, but the L equals 1 spherical harmonics, which are actually just proportional to X, Y, Z, have odd parity. And so you just keep flip-flopping. But I always like thinking about these as Cartesian polynomials because it makes it a lot more apparent, basically the degree of the polynomial. So these are always carrying basically 2 coordinates in every monomial. So you can think of, that's why it's changing it twice the angular frequency. But they have this nice irrep structure. All right, let's get to the pretty pictures. Okay, I want to give you some intuition for why spherical harmonics are awesome, especially when you're dealing with atomistic systems. Atoms don't like to be next to each other. They tend to spread out evenly across kind of the sphere around the central atom, which makes spherical harmonics a particularly good basis, and hopefully I can show you here why. So let's say I want to project, or I want to express this radial distance vector onto spherical harmonics. So what I do, I'm dealing with real spherical harmonics in this case. So what I do is I basically do a Fourier transform. So I'm going to evaluate my spherical harmonics at this direction. The radius doesn't matter for spherical harmonics. And then I'm going to attach it to this basis function. And then, so that's my signal there. And if I then plot this back into real space to see what this looks like by choosing up to some L max, so I'm projecting onto spherical harmonics up to some L max, in this case 6, I get this blob. And in this case, you could show it on a sphere, but what we've done is we've taken the magnitude of the signal and we've made that the radius of the blob. So this is in the same way when you see like p orbitals and d orbitals and those sorts of things, exactly the same trick. You just kind of fold it in and the color is showing the magnitude. So if I were to take this up to L equals infinity, this blob would become extremely pointy. It would become back to a delta function. So we can do this. I'm going to skip this point. We can do this for all 6 neighbors of this octahedral local environment, and we'll get basically identical blobs that are just different up to rotation. Now here's the cool part. What if I want to represent the entire local environment, not just the individual blobs? Well, what I've just done is I've just expressed this in terms of coefficients that span a vector space. So I want to represent all of these together, so I just sum them up. So I just sum over my local neighbors, and I get that. I get this beautiful blobby signal that has octahedral symmetry. And this is what's happening inside the convolutional filters of these types of networks. Now it'll be modulated by radial functions, but this is what the angular piece is doing. So why is this useful? Well, first of all, I just turned a variable number of nearest neighbors. You know, I could have 5 or 4 or 19 nearest neighbors. And I've just converted it into a fixed length vector because I just have all the coefficients up to some L equals whatever. And I'm still able to describe basically the local distribution of the atoms or points. Okay, so let me actually show you what the coefficients look like, because they're also good to look at. So these are all the coefficients up to L equals 6. And what I want you to notice is the first 6 rows are the coefficients for these single points. Now they look like they kind of have a similar pattern, and that's not a coincidence. And it's because basically these signals are just rotations of each other. So certain things might change sign, they might change location, but that's why those patterns kind of look similar. But the thing I really want you to focus on is here. When we went ahead and summed up all those coefficients, we got a lot of cancellations. And so when we look at the local environment of the octahedra, there's no L equals 1 component, there's no L equals 2 component, and there's no L equals 3 component. There's 0. This is what it means for something to be high symmetry. It means you actually require higher angular frequency parts of your signal to describe what's going on. And so this is basically an evidence of a high symmetry local environment, is that you have a lot of cancellation. So I think, if I'm correct, the next slide, yeah. Okay, I get this question a lot. Tess, I don't have perfectly symmetric objects in my data set. Why does this apply to me? Well, here's why it might apply to you. So how robust is this cancellation? So let me go ahead and take my local environment, my octahedral environment, and let me kind of rejigger those vertices a little bit so that it's like mostly an octahedron, but not so much anymore. So I'm going to increase the level of noise, and I'm going to look at how this changes my coefficients. So what we can see is that it doesn't change much. Now, this is not necessarily surprising if we think about this as like Fourier analysis, because what we're seeing is that the low order or the low frequency components of the signal don't vary much with high frequency changes. So we will see more changes here, and we will see more changes in like L equals 10 and L equals 12. But we're not going to see very many changes for L equals 1 to 3. And so this cancellation of terms is actually fairly robust. And especially when you consider kind of that we often do machine learning with like relatively low precision, you could imagine that this is just going to be washed out by numerical error anyway. So if you want to capture high symmetry environments with more than just scalars, basically, if you can only describe this octahedral environment with scalars because you only went up to L=1, you can't distinguish between this and like a cube or a sphere. You can't actually get any angular information from it. So it's kind of an interesting case. Yeah, so I always like to say this, symmetry is not binary. You don't either have or have not symmetry. It's a degree of cancellation. So things can be like almost symmetric, and then you'll still see the effects of symmetry. This, of course, changes when you include dynamics because little changes accrue and lead to big differences, but you need dynamics to do that instantaneously. Symmetry is not binary. Okay, I think I'm going to skip through this. What I will say is that interacting spherical harmonic features leads to some really interesting smooth descriptions. You can do something called the bispectra, which is basically take these coefficients, multiply them times themselves twice. There's the power spectra you may be more familiar with if you are in astrophysics. So you can do the bispectra. If you're with low enough L, it's actually tractable. And what you can do is that you can use it to describe distortions, and those features will also have like really nice smoothness properties. Obviously, I'm kind of blazing through this, but I think one more thing that I want to leave you with, and then we'll go back to questions, is something I want to emphasize is that Euclidean neural networks have kind of similar emergent properties to physical systems. So to kind of maybe give some context is while the actual architecture of an ENN only depends on your highest group symmetry, so Euclidean symmetry, you don't need to specifically encode any subgroup symmetries. They're already in there. So the network preserves Euclidean symmetry. Your input data breaks symmetry to the appropriate subgroup. And there's many different ways for something to have the same symmetry. So let's say I want the symmetry of a square. So I can give it the vertices of a square, or I can give it this spherical harmonic signal that also has a square symmetry. Or, for a rectangle, you can give it the vertices of a rectangle or this. And so these neural networks are essentially playing this game where they're learning how to morph your data into different types of objects that have the same symmetry. So that's at least how I like to think about what's happening in the network. And so, yeah, you basically get this thing called Curie's principle, which was articulated by Pierre Curie in 1894. When effects show certain asymmetry, this asymmetry must be found in the causes that gave rise to them. These networks can't break symmetry. So even if you take an untrained neural network, so these are 3 random models, and you give them these inputs that have a certain symmetry, either a tetrahedron, octahedron in this case, and you look, let's say you have it output a bunch of spherical harmonic coefficients. This is what you get. You get things that have the same symmetry as the inputs. And so this is an emergent property. It's not a prescriptive property. It just emerges from the fact that you are preserving symmetry with your interactions. And I think that's pretty cool, especially from materials physics perspective. We know a cubic crystal can't have a polarization. All of this stuff holds true in the neural network without training. So all the symmetry conditions still hold. So I have various things on symmetry breaking, but I won't go into that today. Let me just touch on open questions, and then I'll leave to my closing statement. So we still don't know the best way to compose these building blocks. Like mathematically, we kind of know what the building blocks are, but there's still so much to do to figure out like what's the best way to use this in use case A or use case B. Equivariant networks have this name for being kind of slow. This is an engineering problem. This is not a fundamental problem. The tensor product in its general case is combinatorially explosive, but it doesn't have to be the case. We can make good decisions and prune those interactions. I also personally, the thing I'm most excited about is equivariant generation. This is a really hard problem to do well, actually. It's very tricky to do generative models in a way that's Euclidean and permutation symmetry equivariant. So I'm very excited about what's going to happen in the coming years about this problem. So I'm going to leave this here, and I'm happy to take any additional questions.
Thanks very much, Tess. Okay, questions?
Thanks for the great talk. So with regards to the rotational symmetry, 1/2 is less than 1, which makes me wonder whether spinor representations have any role to play, especially if you're studying data that like wave functions that are complex numbers?
Yeah, so spinor representations are not irreps of 3D Euclidean space. This is part of the reason why we can't directly observe them. So if you actually do want to deal with spin 1/2, you can do this, but you're going to need to put those representations back in. If you wanted to deal with like magnetization measurements, basically you're coercing spins into a vector object with your Pauli matrices. But you can certainly handle that, but it is not a representation that actually like.
Yeah, I guess if you have a wave function or something, it's a projective representation.
Right. Yes. Yes. So there are ways in which you can do that, but yeah, you would need that additional machinery built in. But you certainly could do that.
Thanks.
Yeah.
Tess, thanks very much. My question is about the radial function. So obviously the symmetries are very pretty in the angular space.
Yeah.
When I've played sort of not neural net games, but similar sort of representation games, when we get up to a fair number of points, every direction out to the next point, if I'm thinking about, an atom type thing, you end up with a different sort of radial basis, and the combinatorics of the radial possibilities becomes pretty overwhelming. And I'm just wondering if you've had if you have suggestions in that.
Yeah, so certainly if you're staying at one single point and you want to go out to very high radius, then it can get combinatorially explosive as well. So we tend to use local interactions for this reason. And as far as basis functions go, we tend to either use Bessel functions or like just simple Gaussians for our radial basis, but I think it's far from explored for that. But yeah, I don't have a good answer for you. If you really want fine granularity for large R, I think that is quite challenging. And yeah, because I guess one thing to add to that is because like as you go further out, you're going to need a higher L to capture the same amount of solid angle or the same amount of space.
Thanks for the great talk, first of all. And on your last slide, you were saying that for future directions, generative modeling is particularly hard potentially with these types of representations. Like, why is that? What's like your thoughts on that topic? Yeah, generative modeling with equivariant methods.
Yeah, I mean, okay, so I should say it. So equivariant models that are currently out, we have diffusion models, but those are usually the case where we put as many points out as that we're going to want. And I find for hierarchical data, like atomistic systems, we may want something a little bit different. But I think, you look at autoregressive models, those break symmetry, those break permutation symmetry. And anything where you're going to want to go from one point to many points, you have to think carefully about how you're going to do that in a way that doesn't impose some arbitrary permutation on the data, or at least I would prefer. It would be more elegant to me. I'm sure people can do it where they're imposing arbitrary ordering, but I think it would be most lovely if we didn't have to. Yeah, thanks.
A great talk, Tess. So I have a question. Like, if you actually don't know the symmetries of the system a priori, or like the symmetry is only approximate rather than perfect. So how do you deal with these situations?
Yeah, so I think there's a lot of literature on how to discover symmetries. I am not an expert on these, and so I won't comment too much about it. But I do find in most cases of data, I've yet to have people give me a good example of a case where they didn't know at least the highest symmetry that their data could be. So at least like in my world of dealing with atomistic systems, this isn't usually the case. But I'm very open to hearing of cases where this is a big problem. For the second case, I prefer to view approximate symmetry. It kind of depends. So the physical laws are not approximately symmetry-equivariant. I mean, okay, I'm going to put like some of the more high energy physics stuff aside, but like we know what symmetries govern like atomistic systems. And so anything that it seems like symmetry is being broken, that's actually a great piece of information because it likely means that we don't have a full characterization of our system. Maybe we're dealing with an experiment that has an anisotropic electric field or something in it. So I actually think that in some cases that it's not really approximate symmetry, it's missing information. So that's my view on it. And I think Robin's going to give a talk later. And I love talking with Robin about these things. So I'm sure maybe he'll have some he'd be a great person to ask this question to as well. Yeah.
So let's see if there's any other questions. I do have a question myself, which is that in my experience, trying to deal with symmetries, you talked about the problem of truncating. You just lose that information.
Yeah.
But another thing you could do is say, well, I know I need to truncate that information. Let me just pre-compute a bunch of invariants that have like combinations of those high L things and just do the pre-computation. So is there any reason why I should not be doing pre-computation? Instead, should really keep the equivariance kind of throughout?
Yeah, this is a great question. And I talk a lot with Soledad about this as she works a lot in invariants. I think that's also a fine approach if you know which invariants to compute. I think in our cases, when we're trying to learn quantum mechanics, we often don't know when we're going to need that information. And so it may be easier for us to leave the information there. But I wouldn't be surprised if people found some effective way of pre-computing invariants that worked most of the time.
Great. Any last questions? Okay, well, thanks, Tess, for great kicking us off.